Hello class. So today I'm going to cover the week of February 24th through February 26th, where we covered Chapter 6, Alkyl Halides, Nucleophilic Substitution and Elimination. So essentially this one lecture will cover all of Chapter 6. The main topics in this chapter are by far the most important in Organic Chemistry 1, I think, are SN1 and SN2 reactions, followed very closely by E1 and E2 reactions, equally if not more so important. And then there's some corresponding properties or topics or concepts that go along with these necessary four reaction types. So one of them is basicity versus nucleophilicity. Nucleophilicity. Then there's polarizability. Then there's rearrangements, specifically carbocation rearrangements. And then Zaitsev's rule. Zaitsev's, that's a V. Zaitsev's rule. And then last but not least, a little bit of an introduction to synthesis, which in my opinion is the whole point of learning organic chemistry, or doing organic chemistry too. So I'm going to do this lecture a little bit different than I did in class. I'm going to do the same topics, concepts. I'm just going to restructure it a little bit. So if your notes don't completely match up with this lecture, don't freak out. It's just, I'm going to just rearrange it a little, that's all. Sometimes it's good to approach topics from a different point of view or just see it in a different order. Sometimes it can help your understanding. So first I'm going to start out with SN2 chemistry, right? So SN2 stands for substitution. I write slower than I talk. Nucleophilic. And the 2 means bimolecular, which means in the rate determining step, 2 molecules are involved. Okay? So a normal SN2 reaction involves some type of nucleophile. You have some type of carbon structure, which we call the substrate. You have some type of leaving group, which generically I'll just write Lg. The nucleophile replaces the leaving group, and you end up with something generic like this, right? That's our overall reaction. It's very, very simple. And it's just one step. And because it's just one step, that step necessarily has to be the rate determining step. The mechanism is really where we start to kind of dig in deep to what's going on here. Nucleophiles often must necessarily have a lone pair of electrons. They may even have a negative charge. Substrates necessarily have to have some type of leaving group. And so a strong nucleophile will do a backside attack on our substrate. I'm going to write that down because it's important. Backside, meaning the opposite side of the molecule that contains the leaving group. An attack is the word we use when we represent something making a bond to a carbon. We call it an attack. And in that same step, the act of making a bond between the nucleophile and the carbon is the same cause that results in the leaving group leaving. When that happens, you get a nucleophile. You get a transition state that looks something like this. The nucleophile is partially bonded to the carbon. The leaving group is partially bonded to the carbon. The nucleophile has a partial negative charge. The leaving group, which is stealing these electrons, and actually that arrow is a little ambiguous, so I'm going to clean it up a little bit. I like that a little bit better. Partial negative and partial positive gives you something like this. The carbon starts out as sp3 hybridized. It turns into an sp2 hybridized in the fleeting moments that it exists during the transition state. And at the end of the story, the carbon ends up as sp3 hybridized again. Something like this. And the leaving group will float around with that lone pair of electrons. Depending upon the nature of the leaving group, it can have a negative charge, it might be neutral, etc., etc. So that's our SN2 reaction and our SN2 mechanism. I'm going to address the SN1 mechanism now and the SN1 reaction. And this is where I'm going to vary from the structure that I did in lecture. For SN1, we have a very similar general reaction. We have a nucleophile, and it's going to substitute its position on the substrate for the leaving group. But it's going to do it in a slightly different way. So we're still going to end up with the same product, the nucleophile bond to the substrate, and the leaving group floating around. Oops. But the mechanism by which it occurs is very different, and so that's what I really want to talk about next. Let's take a look at our SN1 mechanism. In the SN1 mechanism, the most important thing is that the leaving group substrate bond is not very strong. And so instead of the nucleophile coming in and making the chemistry happen, kind of like billiard balls, in SN1 chemistry, the leaving group says, you know what, carbon, give me those electrons. What this necessarily does is gives you an sp2 hybridized carbocation. And the leaving group leaves, taking his electrons, giving it a lone pair, maybe a negative charge, depends on the nature of the leaving group, etc. And then, once the carbocation forms, the intermediate, then the nucleophile can come in and interact with the positive charge of the carbon and give you the final product, nucleophile bonded to the substrate. Because the leaving group leaves is the slowest step in this two-step mechanism, this is the rate determining step. Sorry, I'm like blowing on the microphone, needs to be repositioned. Okay. In the SN2 mechanism, essentially what's happening is that the nucleophile is interacting with, if I just clean this image up a little bit, the nucleophile is interacting with that little tiny lobe of the p orbital. So remember, the carbon is sp3 hybridized, which means each one of these lines really represents the large or major lobe of a sp3 hybrid orbital. Well, an sp3 hybrid orbital, if you remember what they look like, are not just single lobed, they have like kind of a little tail lobe. And so essentially the nucleophile has to get its lone pair of electrons close enough to this orbital to make the bond. Right? That's the necessary requirement for an SN2 mechanism. In the SN1 mechanism, that is not the case. Let me just move this into a different location. In the SN1 mechanism, leaving group is leaving, breaking the carbon-leaving group bond, forming an sp2 hybridized carbocation. The empty positive charge exists in a p orbital. P orbital is symmetrical about this center axis as I've drawn it. And so this lobe is the same size of this lobe. And so there's no reason to suspect the nucleophile ought to interact with one particular lobe versus the other. Both are equally possible. And since both are equally possible, what necessarily happens is that we get a mixture of both stereoisomers if stereochemistry was an issue to begin with. In the SN2 case, because we necessarily have the nucleophile interacting with the, what I'll call the minor lobe of the sp3 hybrid orbital that's bonded to the leaving group, you necessarily get an inversion, meaning 100% opposite, of stereochemistry if there was stereochemistry in the first place. And that also only is true if the nucleophile and the leaving group have the same priority. If there's priority changes, then technically R can turn into R. But for the most part, R's go to S's, S goes to R's. You always get an inversion of the stereocenter. In the SN1 case, because you're forming this sp2 hybridized carbocation, you essentially have a 50-50 shot of which stereoisomer you'll make. And so you'll make 50% of one, 50% of the other, which we necessarily call a racemic mixture. A mixture of two enantiomers in a 50-50 ratio or a 1-to-1 ratio is called a racemic mixture. So that's our SN1 and SN2 mechanisms in a nutshell. What I want to look at now is the four major factors that you always need to consider when you're talking about SN chemistry, nucleophilic substitution chemistry. Four major factors. You have to excuse me, I live next to a racetrack. I don't know if you guys can hear that background noise. Substitution nucleophilic chemistry. It's my silly neighbors. They like to turn their Toyota Supras into race cars. Whatevs. Anyway, four major factors. 1, nucleophile. 2, leaving group. 3, substrate structure, meaning how is it connected in space. And then the last one, 4, is solvent. Now I'm writing these the same way I wrote it in lecture, but I don't want you to mislead you thinking that this is necessarily ordered according to energy or importance or something like that, right? I'm just saying 1, 2, 3, 4 just to list them out, right? So for each one of these categories, there are some specific subcategories that you should look at. Let's start out by taking a look at the nucleophile. So nucleophile, the thing that is going to bond to the carbon using its lone pair of electrons. Right? What type of properties are responsible for making a nucleophile a good nucleophile? A good nucleophile will have high energy electrons. High energy electrons. Why is that the case? Well, if you go back up and you look at the mechanism, which is how we're going to investigate almost all of our organic chemistry from here on out for the rest of the semester, is by examining the mechanisms. What has to happen in order for an SN2 mechanism to occur? The electrons that are in this orbital have to get into the area of space that's occupied by this minor lobe of the sp3 hybridized orbital, and it has to have enough energy to make this bond, right? This arrow right here represents this bond forming, specifically this dotted line, this bond. If the energy of the electrons are not high enough, that bond will not form, because it'll be endothermic, or the equilibrium will say it's not worth it, whatever. So, high energy electrons, definitely helpful. The higher the energy electrons, the better the nucleophile will be. 2. Polarizable electrons. Polarizable. So not only is it enough that the electrons have to be high energy, they also have to be able to move around a little bit in space. That's what polarizability is. It's the ability of electrons to move around in space. So for example, suppose I had an orbital that was really small. It was like that big. Barely could fit those lone pairs, right? The distance in space that this nucleophile has to move such that this orbital can overlap with this orbital is very far, right? It's a very long distance. The nucleophile has to scooch over until these two orbitals overlap. Hopefully it'll have enough energy, and then it'll say, okay, let's make a bond. Consider the opposite case, where instead of having a small orbital, you had a nice big floppy orbital, right? And the electrons can waver all around. Then it's very easy for the electrons to make this little jump, because this orbital is big and flowing back and forth, and it's kind of like a water balloon. You can squeeze it on one side and it'll go over to the other, or you put a negative charge on this side and it'll push the electrons to this side. But there's lots of room, three-dimensional space, lots of volume for these electrons to interact. And so the bigger the orbital, the easier it is for them to do this part of the mechanism, to do this arrow, to make this bond. And so the polarizability, the ability of the electrons to move around in three-dimensional space, is an important factor as well. The more polarizable, the better the nucleophile. So again, high energy electrons, more is better. Polarizable, more is better. And the last one, and this one is kind of tricky to think about, a small molecular size. Molecular size. Now when I say molecular, I'm not necessarily talking about the actual atom itself that makes up the nucleophile, but rather the entire molecule that contains the nucleophilic atom. Right? Up until this point, we've just been using the generic Nu to represent nucleophile. But that's kind of silly, right? And there's no such thing as Nu. We got to actually use real things. So if I had a nitrogen, let's say nitrogen with a lone pair of electrons, I had 3 hydrogens attached as I do in ammonia, I would have a decent nucleophile, right? If I remove one of those hydrogens, so that my nitrogen now has 2 lone pairs, which would give it a negative charge, now I have a really good nucleophile. Why is that? Its electrons are high energy, i.e. it has a negative charge. It's not terribly polarizable because the orbital in which this negative charge exists is an sp3 hybrid orbital, so that's not the biggest orbital. A 2p and a 2s hybrid orbital, so it's not that large in terms of three-dimensional volume. But the molecular size is small, right? We're talking about a total of 3 atoms, 2 of which are hydrogens, right? Those are tiny. So that's small. So this would be a really good nucleophile. Other examples of good nucleophiles would be things like OH-, 2 atoms big, one of which is an H. I-, big, fat, polarizable orbitals, high energy electrons because it has a negative charge. And it's a small molecular size. It's only 1 atom big, right? So these are some examples of good nucleophiles. And there's a bunch that I gave in lecture. Here's another one, for example, right? So those are examples of the good nucleophiles. So they get the smiley face. They all go together. But what do I mean when I say small molecular size? Well, let's compare this molecule. Just by looking at it, would you think that it would do you think that it would be a good nucleophile? Well, you have electrons on an oxygen, which are electronegative, so the polarizability isn't that strong. The electrons are neutral in terms of, the whole atom is neutral, so there's no negative charge, so the electrons are not particularly high energy. And now we're talking about 1, 2, 3, 4, 5, 6 carbons, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens. That's a lot of atoms that this oxygen has to drag around with it if it wants to do nucleophilic chemistry. So much so, it's just not going to happen. Some other examples, like this, right? As you start to pile on the atoms, right, now we're talking about the nitrogen, which is the nucleophilic part, but then we got 5, 6, 7 carbons and a bunch of hydrogens. There's just a bunch of stuff that gets in the way. Dimethyl sulfoxide. The oxygen technically can be nucleophilic because it does have lone pair electrons, but it's a relatively stable molecule by itself. It doesn't have a negative charge. Again, these electrons are in an sp2 hybrid orbital, which are even less polarizable than the sp3s. It's just trouble all the way. Water. Nice stable molecule, good thing because humans like water most of the time. So these are examples of bad nucleophiles, right? Just a couple good, couple bad. So those are the properties that you want to look at when you're evaluating a nucleophile. Sometimes the property of one, like polarizability, will defeat the property of the other, meaning they contradict each other. You might have high energy electrons, but they're very polarizable. Or you might have high energy electrons, but they're not very polarizable. And so one factor will kind of overwhelm the other. When you're evaluating whether or not SN1, SN2 chemistry will actually occur, you have to watch out for you have to evaluate the nucleophile for each one of these properties independent of the other properties, and then see which one is the most dominant factor. Sometimes it's energy, sometimes it's size, etc. So that's where the practice of doing these types of reactions comes in. So that was the first factor, and that applies for both SN1 and SN2 chemistry. Let's talk about the second factor, leaving group. Does the leaving group matter? You bet it does. Leaving group. So there are a couple factors that are also important when you're considering the goodness of a leaving group. And let me just get to my list here. There's two major things. The ability to stabilize the electrons after the leaving group is left. So ability to stabilize electrons after, right? So this is after it has left the molecule. Ability to stabilize electrons after leaving group leaves. The better it is able to stabilize those electrons, the more willing it is to leave, because the more stable the corresponding ion or molecule that you're forming is. And the other one is electronegativity, or electron withdrawing effects. So essentially, does it have electronegative atoms? That's really what you're looking for. Negative atoms. Why do we want them to be electronegative? Because we already said when the leaving group leaves, it takes its electrons with, and so we want to put those electrons in a place that will stabilize them, akin to number one, and electronegative atoms are good at doing that, right? So in class I gave this example. I said here's acetate, where the leaving group will be the oxygen-carbon bond doing this, and compare that to methoxide, where the leaving group will be this. In one case, you get that. In the other case, you get this. Which one is more stable? Well, this one is resonance stabilized. Hopefully we can recognize that by now. And so, because this is resonance stabilized, number one, the ability to stabilize electrons after the leaving group leaves. This is incredibly stable. Resonance is a great thing to be able to do in order to stabilize electrons. And so this is a much better leaving group than methoxide. Methoxide is actually a really terrible leaving group. Okay, so some examples of good leaving groups. Things like sulfate, right? When sulfate leaves, you get O-. Oxygen's negative, electronegative. It doesn't particularly mind having a negative charge. Plus, it can do a whole bunch of resonance with the sulfur and the oxygens. Phosphate, same thing. O-P-O-O-H. OH. Do a bunch of resonance, putting a negative charge on the oxygen. Bromine's not so bad because it's electronegative, and the orbital in which the electrons go are relatively large. Same thing for chlorine, iodine. So bromine and iodine are good. Chlorine is okay. It's kind of in the middle ground. It's like, well, it's not great, but it's not terrible. Fluoride, F-, is in the bad category. So here's our good category over here, and here's our bad category over here. I'm going to put F as in F-. Methoxide is already there. Do I have any other examples that I gave from lecture? It doesn't look like I did. Other good ideas. If you generate water, like a neutral molecule, that's also a good leaving group. Because remember, when the leaving group leaves, it takes electrons with. If you generate a neutral molecule, that's better than generating a negatively charged species, right? Even if it's negatively charged with resonance. So water is also a good leaving group. And we'll see in chapter 10, when we do some dehydration reactions, that water is actually going to be a very common leaving group with our reactions. So those are the properties you're looking for a leaving group. Essentially, what happens to the electrons after the leaving group leaves? Do they get stabilized in some way, either because they're on an electronegative atom or because they're resonance stabilized, etc., etc. Electronegative atoms help. All right, let's look at our third factor. I'm going to go to the next page. Third factor, substrate structure. Alrighty, what do I mean by this? What am I talking about? Essentially, I'm talking about how the molecule is shaped. How molecule is shaped in 3D, right? What's attached to the stuff that has that has the leaving group. So for example, the example I gave in lecture was I take this really good nucleophile, negative charge nitrogen, likes to do chemistry, and I take this pretty good leaving group, iodide, and I do SN2 chemistry as my example. So attack, leaving group leaves, to give me H2N CH3, methylamine if you like Breaking Bad. I also made the same joke in lecture. Haha, I'm clever. And I take the same leaving group, I take the same nucleophile, but now instead of using methyl iodide, I'm going to use T-butyl iodide. So I'm going to replace each one of these hydrogens with a methyl group. And I'm going to draw it in the kind of space-filling way just to point out how stupid this gets. If you make a model with your model kit, you'll see what I'm talking about. This should be a CH. If you're going to do SN2 chemistry here, the nucleophile has to squirm his way in between these methyl groups and attack that carbon, right? And it has to find that little lobe that we talked about. That's not a very easy task for a nucleophile that's negatively charged and all these carbons that are physically blocking its way. And so if you're going to do SN2 chemistry, you would get something like this. But it turns out that because of the presence of all these methyl groups, they're just so fat and bulky, sterically in the way, they're physically in the way, that this arrow does not happen. Therefore, this reaction does not happen. Therefore, this product does not form via SN2. As it turns out, it's better for SN1. We'll take a look at that in a second when we consider solvent effects. Okay. So the more accessible that carbon is, the more likely it is to do SN2 chemistry. And it's actually the opposite trend for SN1. We'll talk about that in a second. Okay, so that's let's see, that's substrate structure, I guess. Is there more I want to say about that? Yeah, we'll make our trends right now. So if your carbon is primary and allylic, A-L-L-Y-L-I-C, it'll react faster than a primary carbon for SN2 chemistry, which will react faster than a secondary, which will react faster than a tertiary to the point where tertiary doesn't even happen at all. And what I'm going to do is I'm going to put 2 of these, meaning tertiary is terrible. Under SN1 conditions, it's the opposite, right? So before I fill in the SN1 trend, let's talk about why it's the opposite. Let's do the same case. Take the same nucleophile, which is a good nucleophile, by the way, and we'll take our methyl iodide, and we're going to do an SN1 mechanism this time. So the SN1 mechanism says he leaves, gives you a carbocation. Then the nucleophile comes in and says, I'd like to react, please. Thank you. 1 reaction, please. And you get this, right? So you get the same product, because there's no chiral center, so you don't have to worry about the inversion and stereochemistry and that stuff. But what's the difference? The difference is you form this intermediate, right? What type of carbocation is this? Primary, secondary, tertiary, or methyl? Well, it's methyl. What do we know about the energy of methyl cations? They're absolutely atrocious, right? It's super high energy to the point where this reaction does not happen via SN1, so you do not get this product via SN1 because you have to form this high energy intermediate, and it just doesn't happen. Instead, the nucleophile will say, hey, I'm a really good nucleophile, and you're primary. I would rather do SN2 chemistry. And so you go directly to product in 1 step to get the product. So it would be the SN2 mechanism. It would not be the SN1 mechanism. Let's do this the other case. So take our nitrogen as our nucleophile, and we'll do our methyl groups again. I'm just going to draw it this way this time to save a little bit of time, because we already saw it before. What's the first step in an SN1? Leaving group leaves, gives you a carbocation. What type of carbocation forms this time? Primary, secondary, tertiary? That's right, it's tertiary. And what do we know about the stability of tertiary carbocations? They're pretty good, right? So this doesn't mind forming, right? It's not the best, considering it is a carbocation, but it is something you can form, right? The inductive effect says, hey, you have 3 buddies, they kind of stabilize that positive charge a little bit, therefore this will indeed actually happen via SN1. Then the nucleophile will come in and say, 1 reaction, please, and you'll get your product, H3C, and H2, CH3. And this only happens via the SN1 mechanism. SN2 cannot happen because of the hinderedness of this central carbon, meaning stuff is in the way. In this case, they're just methyls, but they could be ethyls, they could be isopropyls, they could be cyclohexyls, right? I could easily just erase this and make it a cyclohexyl, right? That makes it even more hindered. So the more carbons and the more junk you pile on out here, the more it prevents SN2 chemistry and the more it promotes SN1 chemistry. And so the trend we end up seeing for substrate structure is that tertiary and allylic is the way to go, and secondary is second best, and primary is terrible, and methyl is terrible as well, to the point where it doesn't even happen. Right? So these are the trends we see. I don't know why this stupid thing does that. Whatever. Right? Why is allylic important in SN2? Right? We said before, the nucleophile comes in, it attacks, leaving group leaves, all in one step, bam, you get your product. Why does allylic matter? Let's take a little bit closer look at that. So I'm going to go back to the SN2 mechanism. I'm going to use the same exact example. In the SN2 mechanism, remember, these electrons are interacting with this lobe of the sp hybrid orbital, and you're getting a transition state that is what? Let's see, it would be H2N dot 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 C dot 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 I H and H, an sp2 hybridized center, right? So we get something that looks like this, which then turns into our product, good old methylamine, which is actually good in nucleophile as well. Okay. If this carbon was allylic, it would be a structure that looks something like this. Allylic means one carbon away from a double bond. So suppose my double bond is here, and I had an allylic structure. I'm going to use the same nucleophile, so I do it scientifically, don't change anything except for the one variable that I'm concerned with. Make sure I have enough bonds on my carbon. Now when the nucleophile attacks, the leaving group leaves, and you form that same transition state, sp2 hybridized carbon, so that, and then one will be there, and then I always like to draw it this way. We get the same thing, H2N dot 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 I. So here's our transition state. Why is this transition state different than this transition state above, right? Why is the second case different than the first case? Remember, it's sp2 hybridized again, so what we're saying now is there's a p orbital that's here, and there's a p orbital that's here. In the transition state, which just exists for a fleeting moment in time, you can't isolate it, this p orbital can overlap with the pi system that is adjacent to it. So if you get orbital overlap here, you get orbital overlap here, the energy of this corresponding p orbital that forms is now a little bit lower than in the top case because of this fleeting momentary p to pi orbital overlap. Right? So the electrons that are in the pi system temporarily get to jump into this empty p orbital and hang out while the reaction is occurring. And just to give you an idea of the speeds that we're talking about, molecular motion usually occurs on the order of 10 to the negative 12th to 10 to the negative 15th of a second, something in there, depending upon the size and the temperatures and things like that. But the time scale of electrons jumping back and forth between orbitals is 10 to the negative 18th, 10 to the negative 21st of a second. So we're talking about, that's what I say, 10 to the 12th, 10 to the 15th, to be a factor of 1,000 to 1,000,000 to 1,000,000,000 times faster, depending upon the specific scenarios. And so from an electron's point of view, it has all day long to jump back and forth and expand and say, and relax until this bond is completely made, and then they have to evacuate back to their pi system, where you get the product, and the electrons are cooped up in their original pi system that they came from. But in the meantime, they get to expand into this newly formed temporary pi system, and that's a very energetically favorable thing to do. And that's why the allylic version for SN2 is more favorable than the just regular old primary. All right, so those are our 3 of our 4. Substrate structure was the 4th, and the last one, solvent effects. Solvent. Speaking of solvent, I could go for some right now. Alrighty, delicious solvent of shock top. Alright, There are three essential major types of solvents that you do SN1, SN2 chemistry in. There's the nonpolar stuff that you already know about. So things like hexane, for example. And it's just faster to write it like that. There are polar aprotic solvents, and there are polar protic solvents. Okay, so polar obviously means you have some type of dipole, some difference in electronegativity between atoms in a bond. Protic or aprotic means does it have a proton, a hydrogen, or does it not? So polar aprotic example would be let's say polar aprotic dimethyl sulfoxide, which I mentioned earlier, or acetone, which would just be 2-propanone, or polar aprotic acetonitrile, where the carbon-nitrogen triple bond, that was supposed to be nitrogen, carbon-nitrogen triple bond, come on, nitrogen, whatever. Right, there's no hydrogens directly bonded to electronegative elements such as nitrogen or oxygen. Polar protic, very simple, most obvious example, be water. Water is strongly polar, and it's protic because of a proton, a hydrogen, directly bonded to an oxygen. Alcohols, anything that has an alcohol has a hydrogen directly bonded to an oxygen. Or an amine, things like RNH2, right? Polar protic solvents because the hydrogen is directly bonded to electronegative elements such as nitrogen. Okay. Why did the solvent matter? Well, think about what's going on in the SN1, SN2 mechanism. If you're doing SN2, right, you have a nucleophile, and you have a carbon that has a leaving group, and you have a one-step rate-determining step reaction. The nucleophiles take its electrons and jam them into this orbital, right? We already said that a million times. But if we're in a polar protic solvent, now we have protons. Let's say we're in an alcohol, right? There's molecules of alcohol over the place. They're just hanging out because that's what solvent does. Hangs out, sometimes gets in the way. What are these electrons going to do? Are they going to try and form a bond to a carbon? Or would they rather maybe just hydrogen bond to the hydrogen that is all over the place? If you said hydrogen bond, you would be correct, right? The hydrogen bonding gets in the way of the nucleophile, right? The nucleophile needs to be unencumbered. It needs to get all this junk out of the way so it could do its job, right? Which is this. Right? If there are these solvent effects in the way due to a polar protic solvent, the nucleophile is hindered. So sometimes you can choose a nucleophile that is too hindered by the solvent. Unfortunately, the opposite is true for the leaving group. Once the reaction does occur, if it occurs, when the leaving group leaves, it takes its lone pair of electrons, right? Maybe it has a negative charge, maybe it doesn't. What do those lone pair of electrons do? They write like someone with Alzheimer's. I can't stand this screen. Right? And the electrons get stabilized by that protic solvent. Right? So while it stabilizes the leaving group and helps it after it has left, it also hinders the nucleophile. And so it's not particularly favorable to have a polar protic solvent for many nucleophiles. If you are going to use a polar protic solvent, right, you want to use a big nucleophile. Let me be a little silly the way I draw this. Consider I had a big nucleophile with a big fat polarizable orbital. Now, when those hydrogen bonds interact with the lone pair, right, there's still plenty of orbital that can do the job. Right? So, hi-ya, right? The solvent just won't get in the way. And so if you had a polar protic solvent like water or ethanol or something like that, iodide and bromide would be much better than if you had a smaller orbital, like a fluoride or a chloride, for example. So as nucleophilicity increases, as size increases in polar protic, PP, polar protic solvents. Okay. With polar aprotic, it's the other way around, right? Polar aprotic. Right, so if you had a nucleophile and you had a polar aprotic solvent, let's say acetone, right? CH3 carbon, CH3 double bond O, right? Looks like that. If you have that, yeah, you have a little bit of the carbons which have a delta positive, because dipole moment, lining up like this. But this is such a weak interaction, right? Because it's just a really weak dipole or moderate dipole, barely interacting with the electrons. You get something like that. It's not enough to stop the nucleophile from doing its job. So the nucleophile's like, whatever, I'm going to attack this carbon. Leaving group leaves, SN2 style. You get the same product that we've been getting all along, right? No big deal. Once the leaving group leaves, takes its electrons with, you don't particularly get much stabilization, right? You get the same effect of solvents surrounding the leaving group, something like that. It's not terribly stabilizing. It's not terribly preventative. But if we were going to do an SN1 mechanism, where the first step was the leaving group has to leave, this bond has to break and go to the leaving group, now we want a solvent that will kind of wedge its way in here and help this to break, right? So when we form an SN1, what are we forming? We're forming a carbocation, super high energy. We're also floating away some leaving group. We want some type of solvent that will help stabilize this positive charge. So what do we want? We don't want protons with H+, right? That doesn't help us. What we want is something with a partial negative, like acetone, for example, because that partial negative oxygen will say, hey, you're positive. I want to hang out by you. Let's be friends. Oxygen's a little lonely sometimes. Right? So you get some stabilizing factor because of the presence of the electronegative element. In this case, I chose oxygen. Right? So that helps stabilize the carbocation, and since the formation of the carbocation is essentially the defining factor as to whether or not an SN1 mechanism is going to occur, the more you stabilize it, the more likely it is to occur, so the more likely you are to do an SN1 mechanism. And so you want an ionizing solvent because you're forming an ion. You want a solvent that helps break this bond. It can squeeze its way in and say, let me in there. Water is really good at this because it could use the oxygens to stabilize this, and it could use its hydrogens to stabilize the leaving group. Right? So water as a polar protic solvent is good for our SN1 chemistry. Wedge its way in there and say, hey, break this bond. You don't really want that bond anyway, right? And then, of course, still get your product, carbon nucleophile. Like that. Alright, so that's what we're looking for when we look for different solvent effects. And like I said before, examples of polar protic and polar aprotic I gave you already. One more, DMF stands for dimethylformamide. Polar aprotic solvent, right? Polar because there's a couple bond dipoles, and there should be a hydrogen for DMF. Acetone, acetonitrile, etc. Alright, so those are SN1, SN2 chemistry in a nutshell, including stereochemistry, meaning inversion or racemic mixtures, nucleophile leaving group, substrate structure, solvent effects. Done. Let's talk about the next topic, E1, E2. E1, E2. E2, not 2. Let's do E2 first. Alright, E2 stands for elimination. And 2, guess what? Bimolecular. So in the rate determining step, you have 2 molecules doing their thing. Whereas an SN1, SN2 reaction gives you a substituted product, an E1 or an E2 reaction gives you an alkene. So let me flip to my page, and we'll take a look. Right? In an E2 mechanism, you're going to start with some base. That base is going to have a lone pair of electrons, and ideally you want it to be a pretty good base. Scroll down a little bit. Okay. And this time what we're going to do, thought that was going to crash on me. And this time what we're going to do is we're going to remove a proton from the position that is alpha. Sorry, let me get rid of this. Position that is alpha, meaning next to the carbon that wears the leaving group. So instead of having a nucleophile attack here, instead we're going to have a base deprotonate here. And I didn't like that arrow, so I'm redrawing it. There we go. If the base removes that proton, because that's what bases do, these electrons are unaccounted for, so they have to go somewhere. They can't just flop around in space. Where are they going to go? They're going to go between the 2 carbons. And since this carbon cannot violate its octet, it says, peace out, leaving group, I don't like you. And in one step, we get our product, which in this case is an alkene. We get our protonated base, because we had used that to grab a proton. And we get our leaving group when it takes its electrons when it leaves. May or may not have a charge, just depends on what it is. That was the E2 mechanism. In the E1 mechanism, it's very similar to the SN1 mechanism. Maybe you're picking up on the trends by now. We're still going to have a carbon at the alpha position that has a hydrogen. But instead of a base coming in and doing chemistry and then bang, 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 instead the leaving group is going to leave. We're going to generate a carbocation. And I shouldn't do that. It's bad practice. After you form a carbocation, then the base comes in and says, well, alright, I suppose I'll be a base. Grab the proton, and the electrons snap down. And what do you get? The exact same product. This is important to note, right? What do we get here? Alkene, specifically ethene, right? Carbon, just a single carbon-carbon. That's terrible language. Just one carbon-carbon double bond. Same thing here. Whereas in SN1, SN2 chemistry, you can look at the nature of the product. Is it 100% inversion of stereoisomer? Yes, therefore SN2 chemistry. Is it a 50-50 mixture? Yes, therefore SN1 chemistry. You can use the product to deduce the mechanism. You cannot do the same thing for elimination, unfortunately. You see an alkene, maybe it was E2. You see an alkene, maybe it was E1. You need other information to to deduce which mechanism actually occurred. And so if you want to do one particular mechanism, there are a couple factors you need to take into account. The key things you need to look for when you're doing elimination chemistry is you need to have a leaving group in the alpha position, meaning the position right next to a carbon-hydrogen bond. Essentially they have to be adjacent to each other. And what else do you need? You need a good base for E2. Alright, just like in SN2, you need a good nucleophile to make the chemistry happen. Just like E2, you need a good base to make the chemistry happen, forcing it to happen. If you have a good leaving group, then the leaving group's just going to say, peace out, I don't care, I'm leaving, giving you a carbocation, and therefore you'll be doing the E1 mechanism. So essentially what you're going to compare is the goodness of the base for E2 chemistry to the goodness of the leaving group for E1 chemistry. And again, this is an apples to oranges comparison, because you're saying, is the base better at being a base than the leaving group is better at being a leaving group, right? That doesn't make sense intuitively. Is my car faster at being a car than my fridge is at being a fridge? Like, there's a weird comparison. So it's not very straightforward, but again, there are things you want to look for. Let's look a little bit closer at the E2 mechanism. Right? When you do the E2 mechanism, I said before, you necessarily have to have a strong base, and you have to remove a proton from the alpha position. And this has to occur. Suppose I was right here, and I was looking down this carbon-carbon bond, and I drew a Newman projection. What would I see? Well, I see my hydrogen on the top. I see my base coming in from the top and grabbing it. These electrons here would be snapping down, so they'd be going down here, so the arrow would be disappearing behind the circle. And the leaving group, in the way I've drawn it here, would go out the bottom, and then these other four lines, 1, 2, 3, 4, would just be 1, 2, 3, 4. Leaving group would leave and take his electrons with. I would get something like that. If you notice, there's a very specific orientation in space that this needs to obtain in order to actually occur. And one of the things I like to point out is that the electrons flow relatively linearly. So the electrons start at the top, they go down, they go down, they go down, so you get this very generic electron flow. Same thing here. Electrons start at the top, they go down, they go down, they go down, like that. They can go up, they can go sideways, they can go in, they can go out. It doesn't matter as long as it's linear. Suppose I drew this a little bit differently. Suppose I drew it like this. And I'm not going to draw it over here because this side of the screen gives me Alzheimer's or something. I don't know what's going on with that. Suppose I drew the leaving group so it was like this. So the base takes these electrons, they snap down, then the leaving group leaves. What has to happen to the electrons? They go this way and then they go that way, which means at this point they smash into each other. What happens to the energy of a molecule when electrons smash into each other? That's right, it skyrockets. So if I was going to draw the Newman projection for this, right, even if I drew it staggered, let's say I drew it staggered, right? I mean, we can say eclipse or staggered, doesn't matter. What would happen? The base grabs the electrons, they go down, then they go out, right? The electrons essentially have to go in and then out. All right, again, the point where they kink, the energy skyrockets, and so this three-dimensional conformation prevents elimination or E2 elimination from occurring. It must necessarily happen in this conformation only. This conformation is called anti-periplanar, or as your book calls it, anti-coplanar. I like anti-periplanar better. Maybe it makes me sound smarter. But anti-coplanar is the same thing. Anti mean they're on opposite sides. The leaving group and the hydrogen are on opposite sides of the molecule. Coplanar means there's one plane that they exist within, right? In this case, they both exist here. Here, there's not a single plane that you can draw that will contain this carbon, this leaving group, and this hydrogen, right? They're all in different planes. There's some type of dihedral angle that is not equal to 0. All right, so this is necessary for E2 elimination. I'll give you a quick example. Suppose I had a molecule like this. Okay, so we have a hydrogen here and a iodine as our leaving group here, and then a hydrogen here and a hydrogen there. Right? If you made this molecule with your model kit, actually I'm going to get rid of this hydrogen and this hydrogen. I'm going to make them methyl groups. So that way you can see. If you make this model, there's no way that this hydrogen and this iodine could necessarily get to that anti-periplanar conformation because the rest of the molecule forbids that rotation, and so there is no reaction for E2 chemistry in this case. So this is a typical test question, right? I'll give you something like this, and I'll say, tell me the E2 product. And if it's not possible, your answer would be NR, meaning no reaction. If I said, just tell me the product, and I didn't specify the mechanism, well then you could still do E1, right? The iodine could still be a leaving group to give you the intermediate that looks like this, which is tertiary, so that's fine. You can still have a base, remove this proton, and snap down. And so the E1 product, which would be the only elimination product you can make in this example, would be that, and that would be fine. So just a couple things to watch out for. So let's go through some examples of good bases, things that promote E2 chemistry. And it's the same rule that you talked about, that we've been talking about for forever for acid-base chemistry, the same ones that you learn in Gen Chem, but now we're going to use the organic version. So T-butoxide, carbon with an oxygen, and we're going to stick a couple methyl groups on this carbon. Why is that important? Because the more carbons you stick on, the more the inductive effect pushes electron density to the center carbon, the more negative these electrons become, and so T-butoxide is actually more basic than OH-. OH- is not a bad base, but T-butoxide is stronger. Some other good E2 chemistries. Bulky. You want them to be big. Why? Because if they're small, they can also be nucleophiles. So what we're going to see is that when we're doing E2 chemistry, we can also do SN2, and we're doing E1 chemistry, we can also do SN1 chemistry. They're going to directly compete with each other. And so if you want to intentionally make an SN2 reaction, you want to choose a base that is only, or excuse me, you want to choose a nucleophile that will only be a nucleophile and not something that will also be a base. And I have an example of what I'm talking about in a minute. Okay. Yeah, let's do this example. This is another example from class. It leads us into our next topic. Okay, so suppose I had this chair structure, and I had a hydrogen, and it had a chlorine, and it had a hydrogen, and then it had a methyl group here, right? If I take a relatively strong base like ethoxide, and I tell you specifically I'm making the, one second. I tell you specifically I'm going to be making the elimination product by using a little bit of heat. There's two hydrogens now that can be removed. The base can come along via SN2, I can make that, remove that one. So the electrons go there, and leaving group leaves, giving you this product. Or the base could remove the electron in the back, so to speak. The electrons go there, and give you that product. Well, I'm just going to draw this flat so it's easier to see. I'll use the same terminology, or that, right? So there's your two products that you can draw. Which one forms? Can they both obtain the antiperiplanar conformation? Well, yeah, sure. This one's axial down, this one's axial up. That's easy enough to say, antiperiplanar. The one in the back, this one right here, axial down, chlorine is still axial up, and so they both can form. Which one actually forms? In order to answer that question, we need to know one piece of fact called Zaitsev's rule. Zaitsev's rule says the major product in a reaction like this is the more substituted alkene. What do I say when more substituted? Meaning more sp3 to sp2 carbon-carbon bonds. So if I had 4 carbons, it would be tetrasubstituted. That would be more stable. So I'll draw it this way. Most stable. Then trisubstituted, which should be more stable than disubstituted, which should be more stable than monosubstituted. Right, and there are a couple different variations of disubstituted. You can have cis, trans, and gem, but for now we'll just worry about that. So Zaitsev's rule will actually be the thing that we need to know and understand to answer the previous question. What's the actual answer to this? What is the product that forms? The most substituted alkene. So this carbon right here has 2 carbon-carbon bonds. This carbon here has just 1, so that's a total of 3. This one here has 1 carbon-carbon bond there, 1 carbon-carbon bond right here, and so that's a total of 2. So this is the major product, which we call the Zaitsev product. Okay, let me give you one quick example. If I gave you this, is this a chiral center, by the way? You should think about that. And I said, that was terrible. I said, what's the product? Since I'm using heat, I know that it's an elimination product, so it should be an alkene. So what I'm going to do is I'm going to go to the alpha position, to the carbon that bears the leaving group. I'm going to see if I can remove a proton. I'm going to see if it can get into the anti-coplanar conformation, and if it can, I'm going to draw the corresponding alkene. So I take this hydrogen, I say, can this carbon-carbon bond orientation give me anti-coplanar? Since this is a methyl group and this bond is free to rotate, the answer is yes. And so that would give me a structure that looks like this. If I make that same argument for this carbon and this carbon, I get this and this. Okay. If I take this molecule and flip it over, it's the same thing as this. If I name this molecule, we haven't learned how to name alkenes yet, but we will soon. If I name this molecule, it would be the exact same thing as this. Right? I can just flip this carbon. This one becomes here. This one goes down to here. This one is obviously still the same there. It's the same structure. So I'm just going to erase it because it's the same thing. So now I have 2 possible answers for the elimination product. Which one is the Zaitsev product? Go up to Zaitsev's rule, the one that has the most carbon-carbon bonds. So 4, then 3, then 2, then 1. Here, if I take this carbon, he has 2 carbons attached. If I take this carbon, he has 1 carbon attached. That's a total of 3. If I take this carbon, he has 2 carbons attached, 1 and 2. If I go to this one, he has 0 carbons attached, so that's 2. So this one will be the major product. This one will be the Zaitsev product. And of course, this one will be the non-Zaitsev product, which we'll give a name later on as well. If I just gave you this and said, tell me the products. Products, plural. And now you would have to draw the alkene I just erased. But is it possible that this can be a nucleophile? Yeah, absolutely. It's small, it's high energy electrons, it meets all those requirements. Can it do SN2 chemistry? Can it take these electrons and smash them into here? No. Why not? This is a tertiary carbon. Can it do SN1 chemistry? Can the bromine leave and give you this structure, and then the nucleophile comes in? You bet. And so what is the substitution product? That one. And does it have any stereochemistry? No, because there are no chiral centers, because this side is the same as that side. So this would be our SN1 product, and this would be the major product via E2 elimination. It would also be the major product via E1 elimination as well, just using a different mechanism. Alright, so that is our E1 and E2 mechanisms. There's, let's see, two things left I want to mention. One is I want to draw this very carefully for you. I had my students, or I had you guys in the lecture, draw this picture the exact same way that I drew it because it matters. So if you're taking notes from this video, make sure in your notes you copy this down with extremely high fidelity, meaning match my atoms and my locations and my arrows as exactly as possible. SN2 competes with E2. Alright, so whenever you're doing SN2 chemistry, it's also technically possible you can do E2 chemistry. And here's the perfect example to explain it. If I had a base, like methoxide, and I have a carbon, what's my molecule? 2-bromopropane. Okay. If the base, or nucleophile, the methoxide, if it's going to act as a nucleophile and do SN2 chemistry, it's going to do this. That looks fine. Secondary carbon, so that's okay for SN2. Bromine's a good leaving group, that's okay for SN2. Methoxide is relatively small, high energy electrons, that's good for SN2. So all signs look to, okay, SN2 is not bad. However, what would happen if methoxide, instead of acting as a nucleophile, decided to act as a base and instead remove that proton? It's a relatively strong base, and so removing a proton is what they do. The electrons would snap down to form the alkene, and then the bromine would leave. Is it possible that you can get anti-periplanar or anti-coplanar conformation with this structure? You bet. And so the E2 mechanism is also possible. The thing that I want to point out here is that the difference between being a nucleophile and therefore doing SN2 chemistry is very, very close. The difference is very small, but it's very close to being a base and doing elimination chemistry. Okay, let's compare SN1. So SN1 competes with E1. Let's take a look at that. This time we're going to have a slightly weaker nucleophile. Right? Doesn't have a lone pair of electrons, or doesn't have a high energy pair of electrons like a negative charge. Molecular size is okay, you know, methyl group not too bad. But we can do similar example, right? So instead of, oh, come on, you stupid screen. I don't know why it does this. I gotta figure this out. It drives me nuts. So now the leaving group has already left to give us a carbocation, which is what necessarily happens in SN1 or in E1 mechanisms. And we still have our hydrogen. If we're going to do E1 chemistry, we're going to remove this proton, and the electrons will snap down. But if we're going to do SN1 chemistry, we're just going to attack that carbon directly. Notice how small of a difference it is. It's running into an empty p orbital here, or scooting over one carbon-carbon bond, approximately 1.2 angstroms in length, and one carbon-hydrogen bond, approximately 1.1 angstroms in length. And so if you do, if you want to do the Pythagorean theorem, go ahead. But essentially you're talking about a 2 angstrom difference between doing one of these and doing the other, when the size of the orbital is maybe 1/3 of an angstrom or so, something like that, or 1/2 an angstrom. So it's a very, very small difference. So if you want to do SN1, you want to make the SN1 product, you have to be very careful about choosing your solvent, your substrate structure, your nucleophile, and your leaving group accordingly. If you want to do E1, you have to choose your base and your substrate structure and your leaving group accordingly. Alright, and that's all I'm going to say about that. I gave a couple examples in class, but I want to be done with it from there. last topic. And then I'm going to go finish my solvent. Intro to synthesis, right? So this isn't in your book, right? This is just J original, so sit back and relax. Essentially what we're at now is a juncture where we'll be able to actually do some chemical reactions. We can do SN1, we can do SN2, we can do E1, we can do E2, but all we've learned so far is to take things like alkanes and through free radical chlorination or bromination, chlorinate them, or NBS in light, for example, allow us to brominate them, etc. That's all we know how to do. Well, this is good because alkanes you can dig out of the ground. That's essentially the starting point for any synthesis, some an alkane. Well, for a full synthesis it is, but whatever. This, chlorine and bromine, and we can also learn how to iodate if we wanted to, those are leaving groups, right? So we can do substitution chemistry with these things, where nucleophiles can come in and attack. We can do elimination chemistry. I was going to write an E, where a base can remove a proton and they can leave. So we can now generate alkenes, or I did it on carbon 2, or substituted products, etc., etc., right? We're starting to open up the door now towards doing a couple different things. Taking alkane, turning it into an alkyl halide, then turning alkyl halide either into an alkene, something has double bond, or a substituted product. If our nucleophile was methoxide, for example, we would be generating an ether. If our nucleophile was hydroxide, we would be making an alcohol. Chapter 10 stuff. We can do a lot of different things with these functional groups, and so we're really opening up the door now towards the ability to do a lot of really cool things. Right? So here's a simple example. Right? We can do some small one-step, two-step syntheses. If I might ask you on a quiz or an exam, make this molecule, cyclohexene, starting with that molecule. And you only need 2 steps to do it, so I'll give you 2 arrows. Well, we don't necessarily know any way to make an alkane turn into an alkene, right? But what we do know is that we can take alkanes and we can brominate with Br2 and HV to give us a structure that looks like this. And if we only consider the brominated monobrominated structures, we get something like this. Well, how do we go from an alkyl halide to an alkene? We just saw that through an elimination mechanism with a strong base, like T-butoxide, we can generate a product. So essentially this is a 2-step synthesis. One of the ways that we would draw a 2-step synthesis, instead of using 2 arrows and lots of space, we would just say 1, Br2 and HV, or 2, I'll use O, TBU, and heat. Right? So we might write it kind of stepwise like this, where first you do step 1, interact with that. The product of that you then take and do step 2. The product of that you take and do step 3, step 4, step 5, etc. As many steps as you want to use. Okay? Another example. Suppose I said, make this molecule from this molecule. And the way I usually phrase it is I draw 3 arrows to say, in as many steps as you want, make this. First thing you would recognize is that, well, this is an alkene, so I know in order to make an alkene, I need to have something with a leaving group, so I can do elimination chemistry. And the second thing you notice is that this methyl and this methyl are not on the same carbon anymore. Whereas here, they both start on the same carbon, but one of these has scooched over. When something scooches over, it's a key red flag for the existence of a carbocation. And so you might say, well, first thing I'm going to do is brominate my alkane, because essentially that's all I know how to do with alkanes. So I can brominate and get that product. And unfortunately, when you brominate, you'll also get a mixture of all these other products, which you'll just throw away because you don't care about that. They don't help you in your synthesis. Now we know we want to do a methyl shift. We want the methyl to scoot over. So we want the bromine to leave and leave a carbocation. So what type of conditions do we want to do? Well, we don't want to do substitution because we don't want to replace the bromine. We want it to go away entirely. And we don't want to do an E2 elimination because then we wouldn't form a carbocation. So we necessarily know that we have to do an E1 elimination, and so we say, well, what type of conditions or things do I need to use to do E1 elimination? I need weak bases, and you need ionizing polar protic solvents. So maybe we'll do it in like water, and since we're doing elimination chemistry, we want heat, and water is good enough as a weak base. So bromine leaves to give you your carbocation, which is secondary methyl shift, give you a tertiary carbocation, followed by water doing its thing, removing a proton from this position to give you your product. So again, it's just a two-step mechanism, or excuse me, two-step synthesis. Brominate, followed by eliminate. But you have to go through all those things that we talked about in this lecture. What is the nucleophile? What is the base? What is the substrate structure? What is the leaving group? Do I have a shift? Do I have to watch out for carbocations? What type of solvent do I want? Et cetera, et cetera, et cetera, such that you can come up with this solution. Right? So that would be an example of a nice simple two-step mechanism. Later on, at the end of chapter 7, I'll do things like this. I'll say, here you go. In 3 steps, give me this product. Right? Well, there's bromines on the molecule, so somehow, somewhere along the way, I have to add bromine. Starting with an alkane, there's only one thing I know how to do, brominate. And then the only other thing I know how to do is eliminate, so E1 or E2 doesn't matter, I get the same product. And then what we're going to see in chapter 7, this upcoming week, is that we can do Br2 and carbon tetrachloride to give us this addition product. And so this is an addition reaction, which is actually chapter 7. Right? So we can start to pile on the things that we can do with alkenes. There's a lot of stuff that you can do with alkenes. Alkyl halides, alkanes, and not really. There's 1 or 2 things you can do. That's about it. Alkenes, whole different ballgame. So that is the end of chapter 6. I've been talking for over an hour, so I'm done. Chapter 6 homework is due tomorrow. I understand I made this video a little bit late, but you should be able to do chapter 6 homework by now. If not, make sure you turn it in on Wednesday. At least get some credit for it. And I'll see you guys soon. Ciao.